integral. Section 15.2 line integrals. Let f be a continuous function defined on a domain D in R2. Like this. Domain D in R2, there is a line. Okay? In R2, there is a domain D. This is a domain, actually. This is a domain. Let C be a smooth curve. C be a smooth curve on D. C be a okay. In R2, there is a domain from here to here and here to here. And this is a C, which is a smooth curve like this. Then, the line integral of f along C is defined as this. We have a function of f of x and y like this. And C, this function moves along the C. This moves along this C, like this curve, like this. Okay. Then, this integral is defined as the Riemann sum like this. Limit sigma and delta, like this, when n goes to infinity. When if the limit exists. So this integral is defined in this way. This integral is called the line integral. The line integral of two variables like this is the surface area of the surface from the curve C up to under the surface. G is equal to f of xy. So when you have a function, when you have a line integral of one variable, you are able to find the line, the length of line. But if you have a two variable function, then this line integral gives you the surface area of what? If we have this function f of xy has this object, then if you integrate that function on this C from A to B, see like this, on this, then what you have? F of xi star, yi star is this, is at some point in here. And delta S is this piece. And the product of those gives you what? Height and base gives us the area of this one. In the very small distances. Can someone add all of them from here to here and make this interval very small? Then what it gives you? The surface. Okay. Here, so the next theorem says the way to find this surface area by arc length parameterization. Okay, here we have learned that arc length S of t can be written in this way with the parameter t in section 12.3. Theorem 2 says if f of xy is a continuous function defined on the domain in R2 and C be a smooth curve C with arc length parameterization in D on the interval, open interval A and B, then integral f of xy ds over C can be written as this f of xy, which is parameterized by t, and ds can be replaced by this one. So we can transform this surface integral to this the integral over one variable t, like this. Okay, here is an example. Suppose we have a function f of, if we want to integrate x plus y on S over the semicircle. So what it means is the x is equal to cosine t, y is equal to sine t, and t moves from 0 to pi. Then integral over x plus y can be written as what? Square root of it's a unit circle, so r is equal to 1. So x is equal to cosine t, y is equal to sine t. So cosine t plus sine t is here. Then square root of the what? dx dt. So derivative of cosine t is a minus sine t, the square. And derivative of this sine t is a cosine t, so square of it over the square root, in the square root of 2. So just integral of this one is the what we are looking for, which is 2. That can be shown in here. Okay, here, so we have a unit circle first, and we want to integrate the function xy, which is x plus y, on this domain, on this circle. Okay, we want to integrate this function on here, from here to here. Okay, from here to here. Okay. Then, so here's a cosine t and sine t. X is we know x is a cosine t and y is a sine t, and dx here, dy is here, and ds is what? Square root of dx square plus dy square. That's it. Over the t. Okay. So we all we have to do is just integrate x plus y times ds from 0 to pi. Then this gives us the answer, which is what? 2, as you see in here. That's it. Okay? So if you just formulate it in this way, if you just substitute in like this, then this one variable integral can be easily computed. And next, evaluate x plus y ds, x plus y on a whole circle, cosine t, sine t from 0 to 2 pi. What will be the answer? Okay? This is same thing, same integral from where to where. It's exactly same thing, same code, and same thing from 0 to 2 pi instead of pi. Isn't it? Then, what will be the answer? This is closed interval, which gives us what? 0 as an answer. Like what you get by your computation. Isn't it? Okay. A curve is said to be closed curve when the end point coincide. When end point and initial point is same, then we call it with closed curve. That is, this C is a closed curve if C of A is equal to C of B. If C is a closed curve, then this line integral is denoted by like this. Integral over C on C with the circle. If you do the integration on a closed curve. Okay. So this, okay. Okay. Next. Then, now we study the properties of line integrals of vector field. Let F is a function of the vector. Let F be a vector field. Okay. A function of 3 variables, a function of a multivariable, and the image is in the R3. Okay, if we do the integration on this C from here to here, and if we go this other direction, we call this C means we goes from this initial point to the terminal point. Minus C means we start from this end and come back to the initial point, the origin. Like that. Okay, anyway. This can be written as what? This f of r can be written in this way, and can be written fr dr can be written in this way, and this also written as dx dt and times dt, and dy can be written dy over dt times dt like this. So this can be written as f of r of t times dr over dt times dt like this. This can be written in this way. Okay? Okay. Okay, so this can be written in this way with the parameterization of t. When f1, f2, and f3 are all functions of t. If this, with this integration, the definition of integration, we can have these properties. The scalar multiple can come out, its homogeneity, and its linearity hold, and if the C is consist of the sub-enable C1 and C2, then we can split in this way. If C is the sum of two curves, then we can split. If integral minus C, if we are looking for this one, then this is finding the integral of this one and multiply minus 1. This is minus C is a curve traversed in opposite direction of C. Yeah. If C moves from here to here, then minus C moves from here to here. That's the difference. Okay, next example. Find the line integral of f of xy, which is sine x cosine y I plus exy j along this horizontal line. The second problem is do the same thing along the vertical lines. The horizontal lines is C1. This vertical line is C2. Okay, we are looking for the integral of f dr on C1. Okay, so here, first on this problem, C1 is from here to here and here to here. This f times dr can be written as what? As we see, this vector function times the like what you see. We can write things like this as a dot product. So we write this function and the vector, this vector and inner product, dot product. This is written as what? Sin x times cosine 3 pi plus this times 0, which is 0. So we only have this part on C1. So this value is what? 1/2. This is 1/2, so we have 1/2 sin x to integrate from 0 to pi because x moves from 0 to pi. So we do the integration like this, which gives 1. But on C2, here we have this inverse. So the same functions, so at each point, and x is equal to along with this. So we plug in x is equal to 2 here, which gives us this function. So and then the path is what? From here to here means from 0 to 1. So from 0 to 1. So x direction is 0 and y direction is 1 here. We are moving from here to here. So this is r vector and this is the f of 2y is a function. So if we do compute, then the first, this inner product gives us 0 and this 2y times 1 gives us this left. So we do an integration on dy from 0 to 1. So we do the integration from 0 to 1 e to the 2y times dy from here, which gives us 1/2 times e squared minus 1. This is what we have. Okay. Next example is on what? Three-dimensional functions. We see the similar one for two-dimensional function. It's also this arc the length parameterization gives us the parameterized substitution of t on this function on three-dimensional functions. So we use this one for the example 4. Evaluate integral y square on C, where C is a circular helix given by a vector equation like this. This C is we want to integrate this y square on this curve. This is what we are trying to do. Okay? From 0 to 2 pi. So we do integrate y square ds. So y is in this case x is what? X is cosine theta, y is equal to sine theta. X is so this the substitution is x is equal to cosine theta, cosine t, y is equal to sine t, and g is equal to g. And with those substitution, this y square is a sine t square, and the square root of this dx dt is minus sine t, dy dt is cosine t, and dg dt is 1. Okay, so we have this one. So now we have the integration of single variables like this. We just simplify this, which is this, and this simple calculation gives us square root of 2 times pi that you can check in here. So plot the domain first and do the integration, line integral of y square. Then first do the plot. This is from where to where? From 0 to 2 pi. I do the integrate from 0 to 2 pi of y square and the parametric prop of those r function from t start point to t end point, which is 0 and 2 pi. If we make this one as a 8, then we will have the helix like this, isn't it? As a curve. Now do the integration, line integral, and do the same thing like this. then we have integral which is 2 pi square root, etc. And pi times square root of 2, which was what we are looking for. Okay, I think that's it for section 15.2. Any question on section 15.2 before the next section?